assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
So first, consider that the length of the spring is some value L. So we can say length of spring, this is going to be L, and this would be its relaxed, or rather we can say rest length. We can then say the length of the spring L with one of the block's corners directly above the block center. So if the constant distance between the block center and the point on the wall where the spring attaches is a distance r, we can then say that r cosine of theta is equaling d over radical 2. And again, r is defined as the constant distance between the block center and the point on the wall where the spring is attached. Now, we know that then r cosine is equaling L, and theta, this essentially defines an angle theta measured line on the block drawn from the center to the top corner to the line of R. So essentially a straight line from the center of the block to the point of attachment of the spring on the wall. In terms of this angle, the problem essentially just asks us to consider consider the dynamics of the problem, how the system moves, resulting from increasing the angle theta from its original values. So we are going from theta, the original value of theta, to theta plus 3 degrees. Now, we're then going to release them and let it oscillate. So we're going to say that its new stretched length, L prime, would be stretched length of spring. Then we can simply use trigonometry, and we can say that L prime quantity squared would be equal to R squared plus D over radical 2 quantity squared minus 2R multiplied by D over radical 2 multiplied by cosine of the original angle plus 3 degrees. This is going to be equal to L squared plus D squared minus D squared cosine of 3 degrees plus radical 2 LD sine of 3 degrees. Now, at this point, this is from knowing that the original angle is 45 degrees. So we can then say that the difference between L prime and the original spring length L, the rest length, is the amount the spring has been stretched. So here we can say that the maximum displacement would be amount of, we can say that maximum, let's say x sub m would be we can say amount string has been stretched. And this would simply be L prime minus the original rest. We can plot, if one were to plot the maximum x sub m, the max placement, versus over a range, we can say plotting x sub m versus L, where we have 0.03 meters to essentially 0.10 meters. That seems reasonable. We can see in the approximate, the amount that the string has been stretched would be equal to 0.00222 meters. This is a very good estimation. And essentially, using this value of m with the given spring constant, we can then say that the potential energy would be equal to 1/2, the maximum potential energy would be equal to 1/2 times the spring constant times the maximum displacement squared. We know that the spring constant K is going to be equal to 1200 newtons per meter. And then we can say that the potential energy is going to be 0.00296 joules. We're going to equal to the energy of the block as it passes through the initial position. So we can say that this is going to be equal to the kinetic energy of the block, and this is going to be equal to 1/2 times the moment of inertia multiplied by the maximum angular velocity squared. We can then say that we're going to say the maximum angular speed, let's just say, and we can then say that the rotational inertia of the block I would be equal to 1/6 times the mass times d squared, and I is then going to be equal to 0.0018 kilograms meters squared. So now we can solve for the maximum angular speed, omega sub m. This would be equal to the square root of 2 times k divided by the moment of inertia. So this would be the square root of 2 times 0.00296 joules. This would be divided by the moment of inertia, 0.0018 kilograms meters squared. And so this is equaling 1.81 radians per second. So we can then say that the angular frequency of the oscillation omega would be equal to the maximum angular speed divided by the initial angular displacement. This is going to be equal to 34.6 radians per second. Then after this, we're finally going to use equation 15.5 and say that the period is going to be simply equaling 2 pi divided by omega, the angular frequency of the oscillation, and this is going to be equal to 0.18 seconds. This would be our final answer for the period. That is the end of the solution. Thank you for watching.